And thank you everyone for joining our session, How JPEG Works. Yeah, and I posted a link to the slides up in the chat, which I think you can all see. But let me know if you need that link again, because there's a few links here that you may be interested in. So my name is Omar. I currently work as a graphics engineer at Snapchat on the map. I'm based in Ithaca, New York. It's upstate New York here. And I grew up in Egypt. And I have a background in making video games. That's kind of how I got started, programming in general, but with programming in this specific type of work I do, which is kind of related to what I'm talking about today with image processing. But what I do more generally is working in computer graphics. Yeah, and you can find more about me or reach out at any time at my website here. So what I really want to do today is I want to talk about JPEG, but why are we talking about JPEG? And what I want is to give you a little bit of an introduction about the field of like image compression and image processing in general. And like if you were to choose to work in this field, what type of work would you be doing, and what kind of stuff would you be working on? So that's kind of one takeaway I hope you'll get from today. Um, the other one is even if you're not particularly interested in working in these specific fields, I think it's worth understanding and learning about this sort of thing because it's so ubiquitous. Like if if you're on the internet and if you're on any website, and most of the images you've ever seen on the internet are JPEG images, and so it's kind of everywhere around us, and we kind of take it for granted. But there's a lot that goes on into that. Image compression. I think it's interesting to just learn about how it works and then feel a bit more empowered to understand like the stuff we all use every day. So I think that's cool, but also because JPEG, as we'll see in a bit, is a lossy compression. That means it throws away some information. It doesn't fully retain everything in the original image. That means learning about this algorithm, learning about what it chooses to throw away means learning about human perception and how like the biology of our eyes work, because in order to figure out what things we should throw away, we have to know a little bit about how the human eye works. So I think that makes it kind of really interesting mix between like computer science and biology and color theory, and so it's a kind of an interesting interdisciplinary algorithm here. So I want to also talk a little bit about some applications that I found interesting, and I mean I want to start with the obvious one, why you want to do image compression. Well, you make the images smaller, and that saves you money, so you don't have to pay as much for storage costs, and websites load faster if the images you're downloading are smaller. So that's the obvious one that applies to everywhere images are used. But some particularly interesting ones that I've worked with in past jobs is like satellite imaging. And this one is interesting because a lot of times you don't just want to compress these images in any way. It depends on what you're using them for. And this is interesting to me because sometimes people want these images uncompressed because they want the original data exactly as it was, because they're doing some real world analysis with it, so they're making decisions about where to grow crops or where to any kind of land analysis. And this is interesting because so the U.S. government collects once a year, there's one specific program in the government that does this satellite imagery for the entire U.S. and they give it out for free. What's interesting to me about this is these satellite images, even though they're freely accessible and it's paid by the government and everything, you cannot download them anywhere. Because they're just way too big. So if you want them, you basically have to write to the government and request one, and they'll ship you a hard drive. They'll ship you a physical hard drive with the satellite imagery, because it's just so massive. And this is happening. This isn't like 20 years ago. This is happening. This is still happening today, and people are shipping these hard drives of images. So this is interesting because it makes me think like what a world without compression could look like when the data is so big that we can't you just can't send it over the internet. So you and me could be without compression. If you want to send someone the latest pictures from your trip, you mail them like a little USB drive. So I thought that was pretty interesting. Another one I think is pretty cool, and this is a good kind of example of why it's worth kind of peering inside like how a standard algorithm like JPEG works. as I think this article is worth reading. But basically, this is an article about how Facebook sped up loading profile pictures on devices where there's limited internet, or if you're out on mobile data and you have limited bandwidth. And basically, they kind of like hacked the JPEG algorithm where they removed bits of it. So essentially, like customizing the JPEG algorithm to make it faster for these specific situations. So that also could be an interesting use case, because this does happen where knowing enough about the algorithm, the standard algorithm, maybe helps you figure out specific cases on your data or in your work where tweaking it or doing something inspired by it could be better than just using the standard thing. And the last one is kind of this digital heritage. This is one example. The Smithsonian Museum has been, for the last few years, like digitizing a lot of their collections. They have like millions of paintings and 3D objects. And it's a similar thing here, where you don't, because some of these things are actually used by archaeologists or people doing these studies on them, you want to preserve the images using a compression that retains the original information as much as possible, but also stores it in as small amount of space as possible, because you don't want to spend all your budget on just image storage. So they have like experts. Some people's field of work is to sit there and figure out how do we store these images in the best way. So I think that's also a cool kind of field or kind of type of job you could be doing here. All right, so hopefully that it motivates you enough to feel like, okay, this is worth thinking about. So let's kind of start from the beginning here. If we wanted to store an image on a computer, what do we need to do? What actually do we need to store? How much data do we need to store? So if we think about this image here with the cat, it's a 300 by 300 picture, and it's stored as 3 colors. This is how typically you would store an image: red, green, blue. So that means if each one of those colors is stored as a single number between 0 and 255, which means it's a single byte, then the whole thing, 300 by 300 times 3, it's going to be about 270 kilobytes. Not very big, but if you get the JPEG version of this image, it's 16 kilobytes. So it's 15 times smaller. So obviously there's a lot going on here that could make this image smaller, but we can start to think about what's one thing we can do to make an image like this smaller. We could kind of simplify this even more. What if you had an image that was just completely black square like this? In theory, you would, it's still the same number of pixels. It's still 270 kilobytes. JPEG for this one will give you 2 kilobytes. But I think we can do better. Like, how would you store this image in as few numbers as possible? And if you have ideas, feel free to post them in the chat. I'll give you kind of like a minute, or maybe 30 seconds to think about this. There's a couple ways to do it too. Like, think about what's the minimum amount of information you need to store, and how would you store that, or what's one way you could communicate that. Yeah, see, Michael said something that image dimensions, which is a really good hint to think about. What do you really need to communicate to tell someone? It's a 300 by 300 image. That's black. How much bytes could you reduce that to? Yeah, it's basically it. You want to store, as people in the chat are saying, you could basically say, in the same way I'm communicating to you that this is a completely black image, you could say, you'd have the color, and you could have how many times to repeat that color. And we can do a little bit experiment here that I wanted to show you to kind of get some hints about how an actual JPEG would work. So real quick, what I have here is I opened. So this is the image on my computer, and on the left here I opened it in Notepad++. I didn't do anything special here. I just like file open, and I opened the image file as a text file. And here, what I'm looking at is basically the raw bytes that store a JPEG. And this is actually how I initially learned about this, because I was opening this and I was kind of messing with the bytes to see what would happen. So one thing I could do is just if I delete a few bytes here and save, you can see just by removing like a couple of essentially bytes or numbers on the left here, it messes up the entire image, which is interesting. It kind of gives us this hint that people in the chat were talking about, that we have this repeated algorithm that tells it, yeah, here's another one. I just moved a single number and mess up the whole thing. But also, it only messes up like the lower half. You can see it doesn't touch the top half, which maybe tells us that JPEG does something where it always says like, okay, the next, if this is how this number is repeated in the subsequent pixels, but not before that. One thing I just want to point out here that I think is really interesting about what we just did is that what we were doing there is we were opening a text file. We're opening an image file as a text file. And what this kind of tells us is that everything on a computer is stored as a list of numbers that we call bytes. And those bytes don't really have like an inherent meaning. They can be interpreted. How they're interpreted depends on how you, like, you can choose how to interpret it. Like what we just did here, I chose to interpret the image bytes as a text, and that, even though the text looked, didn't look like any meaningful text, but it was still text I could see and edit. And this is interesting to me because this is very similar to how our brains work. Our brains have the same thing where everything communicated in your brain is coming in as electric signals. So there's no difference between the signals that come from your eye that communicate vision to your brain and the signals that come from your ear that communicate audio. The way the brain knows that it should interpret these signals as vision or audio is based on where it's coming from. So again, there's nothing in the signals that tells it that this is vision or not. Which also means that we can do the same thing we just did on the computer in our brains, where you can kind of swap the signals. Which one way this can happen is if you like rub your eyes, like sometimes you see these like floaters in your eyes, like these little spots that kind of go away after a little bit. What's happening there is like the pressure you're applying to your eye is stimulating the receptors in your retina in your eye, and it's sending these signals that the brain assumes it must be vision because it's coming through the optic nerve. So that's kind of what file extensions are. They're just kind of hints. There's nothing kind of magical or inherent about it. So I just want to point that out. But basically, yes, as we discussed, why would deleting a single number here kind of mess up the whole image? Well, it's because we have this repeated compression, which is called run length encoding. So you could apply this. It's not unique to JPEG. If you have like a list of numbers, like instead of saying 000000001, we can store this as the value and how many times it's repeated. I think I said the important thing at the beginning here, which is how run length encoding works. And the last part I was saying was the minimum I think we need for the black image is about 5 bytes or 5 numbers, which would be the color, the RGB, that's 3, and then the width and height, so it'd be 5. Okay, so looking at another thing that you can compress is the color, because a black and white image is going to be 3 times smaller than a color image, because instead of storing RGB, we just need to store like brightness. I think I'll get back to the run length encoding because we're running short on time, and I want to show you some of the other really cool things. But the takeaway for this one is our eyes are not equally sensitive to all the colors. We're generally more sensitive to red and green, followed by blue, and we're generally more sensitive to changes in brightness than any changes in color. So we can use this fact to kind of choose what information we can throw away. Now, if we're just using RGB, that means we have to choose one of them. Like we could compress like the blue a lot more than the red channel, which could work. But generally, what people with JPEG are going to do are they're going to use another color space where they can compress the color separately from the brightness, which is a little hard to think about. But the storing images in this way is no different than like these color spaces. It's just another way to store the color such that when you combine them, you still get the original color back. So like another easy color space to think about is like the CMYK, which is like what printers use. If you have printer ink, you have like cyan, magenta, yellow, and you can combine them to form any other colors. So YCBCR is another one where the Y is the luminance, it's the brightness. The CB is they call it chroma blue, and the CR is chroma red. And those, the CB and CR together can kind of give you any color, and then the Y tells you how bright that color is. So a quick demo here. So what I want to do here is like convince myself and convince you that this is how our eyes work, and you can actually do this experiment yourself to see which colors your eyes can see most. But the way this works is I have this table, this grid here, and each picture here, when I move the slider below, is going to remove that component. So at the extreme end, if I just pull this all the way, the top left image here removed all the red. The middle one removed all the green. The top right removed all the blue. In the bottom row, this one removed all the luminance, all the brightness. So what's left is just like this raw color that's all like very gray, so you can't really see much. And the other ones are removing. This is removing the blue chromance component, and this is removing the red chromance component. The interesting part here is if you focus on just like the top row, you can see, like, think about which one with some like maybe 25% compression looks best. Whoops. And you'll notice, yeah, you'll notice that you can very clearly see the green, and maybe I'll make it even bigger so you can see it on the video chat here. The green one looks obviously, you have these artifacts, you have these blocky artifacts. I think you can see it in the red one too, but the blue still looks pretty fine because it's just harder for our eyes to like see these changes in blue. Whereas if we compress the luminance first, which is the thing our eyes are most sensitive to, like it's just more obvious to see. Obviously, this looks terrible. You already see, just 35% compression looks really bad. But the bottom two still look pretty good. So this is actually what JPEG does. We pick essentially the bottom two and compress those more than anything else. And this is essentially how they found it. They did these experiments with a lot of people in the 1980s. And they decided, okay, this is based on this is how the human eyes work, and so we're going to compress it this way. All right, so this is the most interesting part of JPEG. What else can we throw away? So think about when we were talking about removing colors that are solid and are like a complete black image. So we can kind of look for something like that. Like if you have an image with like a lot of blue sky, like maybe we can remove a lot of compress a lot of blue color as a big block, and that's great. But we also want to do that not just with the color of it, but also with shapes. So imagine something like, maybe you have a line that is pretty much straight, but has like a few local variations, like maybe take an image of grass, and if unless you zoom in really a lot, you can't really see the individual blades of grass. So maybe we can like smooth these out. Maybe we can average them or make the grass like almost straighter, and that way there's less information in the image. So that's that's the last step we're trying to do here. And to do that, and this is just kind of a visual example here. So this is, on the left is the original JPEG image, and on the right is one which I used like maximum compression on it. And so you can see it looks you can maybe see the artifacts. I don't know if it's coming through very well in the video, but that's why I'm hoping you can see it in the slides. On the cat's face, it's very obvious, but maybe on like on the pillow here, it's not as obvious because it already was kind of like a big block. So smoothing it out doesn't show anything. And just kind of zoomed in more on that. So how are we gonna like smooth out shapes? Well, the way the JPEG does this is using what's called this discrete cosine transform. So this is, you can think of this as just a way of representing any image as a sum of components, and then you can alter these components, remove some of them, and then reconstruct the image. And that way, and the idea is these components give you some control over the shape. So what does this mean? These are the components. There's 64 components. It's a grid of 8 by 8 squares. And the idea is by combining these 64 components, I can create any image that can be made with 8 by 8 from 8 by 8 pixels, which seems a little crazy and magical to me. But as an idea, like, if you wanted to combine those two that I have highlighted in red, it would look, like this. You would take a little bit of each, and you get this like gradient that, like one is a horizontal gradient, one is a vertical one, and you get something that's kind of in between. So it sounds a little magical, but this is really no different. It's called a basis linear algebra, and this is no different from saying that any point in space can be broken down into 3 steps, or to like 3 components. How much should you step forward? How much should you step right? How much should you step upward? And um, and each of these can be negated too. So you can step forward right, but also step -1 right, so you can go left as well. Yeah, we're running short on time. I want to answer some of the questions you guys are asking, because they're really good questions. But thankfully, again, you have this demo here, and this is the last step. And this is definitely worth playing with on your own. But this demo, just to explain what it does, it allows you to click on any pixel in this image, and you'll see it broken down into these components, and then you can edit these components essentially. And I think I'll show it to you on an image of text, because that makes it a little easier to see. So I can drag and drop any image here, and then I can click on this S. So this S is made out of these components. You don't always have to use all 64 components. So if I move the slider here, I can remove some of these components, so I can see how they contribute to it. So at the far end, you only have this one component, and then I can keep adding more and more and more. So it starts looking kind of like an S with just like these first 6. So this is actually one way to compress it. Like maybe I could just choose to use these, and all these zeros that you see, this is the components. So if I change a number here, that's me adding like a component. But if you have all these zeros, you can compress them with run length encoding, which we talked about before, because it's one big block. And yeah, and this applies to any image, and you can try this yourself. And the link, I'll post that. Yeah, it's in the slides there. So this is kind of the 3 steps, the 3 layers of JPEG. You have this compressing the color, the chromatin subsampling, the discrete cosine transform, where we kind of smooth out the shapes to convey it using less information, less bytes, and then the rest of it is compressed with run length encoding. And so a lot of times, yeah, how you want to compress the image, as you see, like it depends on understanding, the human eye. And yeah, I was gonna talk more about that, but let me pause here and look at some of the questions. There's a question Ben asks: how does it determine which of the 64 blocks to use? That's part of the discrete cosine transform algorithm, which is essentially the same thing as a Fourier transform. And it may be, actually, if you're curious to understand this, I'd start with the Fourier transform, because you can do this on audio, and it's a little easier to understand in that case. But in that case, you're trying to get, okay, given an audio file, you want to break it down into frequencies, because this is essentially what's happening. We're breaking an image into frequencies. Yeah, so that's the analogy, and yeah, you should check out Fourier transform and see how that works, and you can kind of see the analogy here. Oh, a couple people are asking about how we're compressing the color. We're basically, it's not quite the bit depth. It's basically, instead of storing, if you have a 300 by 300 image, instead of storing, let's say, the red channel for all of them, you could store it for half the image and kind of average it. So each pixel, so each 4 pixels can have 1 red value if you're compressing the red one. So it's almost like you're averaging it. So that way, if you do that, then you've compressed it. You've removed a quarter no, you've removed 75% of the red if each 4 pixels share one red value. So that's how you would do that. Okay, I think those were the main questions. Yeah, sorry I kind of went through this a little quickly, but this JPEG article is an article that I wrote that kind of goes through what I talked about here today in more detail and with a lot more interactive diagrams that you can try on your own. And the JPEG sandbox, you can drag and drop any image and do this same experiment too. So yeah, thank you for coming, and hopefully you find these resources helpful, and hopefully I give you a little taste into this. And I'll let you go because I know there is another session happening now. But yeah, thank you all for coming.